Hello everyone. In the previous lecture we have discussed about the conservation of linear momentum in case of a system of single particle and also in case of a system of two particles. Now we shall know about the Newton's law of impact, and we are going to discuss or derive an expression for the loss of kinetic energy in case of an inelastic collision. Newton described the elasticity of collision by considering the velocities of the system before collision and velocities of the system after the collision. Here u1 and u2 are the velocities of masses m1 and m2 before collision, and v1 and v2 are the velocities of the masses m1 and m2 after the collision. The difference between the velocities before collision is called velocity of approach, and the difference between the velocities after the collision is called velocity of recession. Newton defined a quantity called coefficient of restitution. It is defined as the ratio of velocity of recession to the velocity of approach. That is, coefficient of restitution is represented by the letter small e and is given by the ratio of v2 minus v1 divided by u1 minus u2. Here, for a perfectly elastic collision, the coefficient of restitution is always equal to 1. For perfectly inelastic collision, E equal to 0. And for the collisions between elastic and inelastic, E lies between 0 and 1. If the value of E is close to 1, it suggests that very little kinetic energy is lost during the collision. That is, the amount of kinetic energy lost is very small. On the other hand, if the value of coefficient of restitution is close to 0, it suggests that a large amount of kinetic energy is lost. That is, a large amount of kinetic energy is being lost during the collision. This loss in kinetic energy will appear in the form of sound, or in the form of heat, or in the form of light, or in the deformation of the colliding system. This is known as the law of impact. By knowing the law of impact, we shall derive the expression for the loss of kinetic energy in case of an inelastic collision. A collision is said to be an inelastic collision if the kinetic energy is lost in the collision. But we all know that the linear momentum is conserved in all types of collisions. The loss in the kinetic energy will appear in the form of heat, light, sound, or in the deformation of the colliding system. The forces of interaction in case of inelastic collision are non-conservative in nature. The most of the collisions which happen in macroscopic bodies are inelastic in nature. Macroscopic means the bodies which are visible to us. If the colliding bodies stick together after the collision, then the collision is said to be a perfectly inelastic collision. Here we are going to consider a collision, inelastic collision in one dimension. A collision is said to be one-dimensional inelastic collision if the colliding bodies move along the same straight line before and after the collision with some loss of kinetic energy. Since the momentum is conserved in all types of collisions, we write initial momentum of the colliding system equal to final momentum of the system, that is Pi equal to Pf. Here Pi equal to m1u1 plus m2u2 and Pf equal to m1v1 plus m2v2, which is the final momentum of the colliding system. Also we write the coefficient of restitution E as equal to v2 minus v1 u1 minus u2, that is the ratio of the velocities of recession to the velocity of approach. From that we shall write the final velocity of the colliding system of mass m2 equal to v1 plus e into u1 minus u2, that is v2 equal to v1 plus e into u1 minus u2. Then equation 1 can be written as m1 plus m2 equal to m1 v1 plus m2 into v1 plus e into u1 minus u2, that is m1 u1 plus m2 u2 equal to m1 v1 plus m2 v1 plus m2 u1 into e minus m2 u2 e, which implies m1 u1 plus m2 u2 minus e m2 u1 plus e m2 u2 equal to m1 v1 plus m2 v1, that is m1 v1 plus m2 v1 equal to m1 minus e m2 into u1 plus 1 plus e into m2 u2. Here we have taken u1 common from the terms e m2 u1 and m1 u1, and we have taken m2 u2 common from the terms e m2 u2 and m2 u2, which implies m1 plus m2 into v1 equal to m1 minus e m2 into u1 plus 1 plus e into m2 u2. Thus we have the velocity of v1 equal to m1 minus e m2 into u1 plus 1 plus e into m2 u2 divided by m1 plus m2. This is the velocity of body of mass m1 after the collision. Similarly, we shall write the velocity of body of mass m2 after the collision as v2 equal to m2 minus e m1 u2 plus 1 plus e into m1 u1 divided by m1 plus m2. If the collision is perfectly inelastic, then the coefficient of restitution is equal to 0, that is the value of E equal to 0. Then V1 equal to V2, that is V1 equal to M1 U1 plus M2 U2 divided by M1 plus M2. Since the collision is perfectly inelastic, V1 is equal to V2, which implies that after the collision both the bodies stick together and move together with the same velocities, that is V1 equal to V2. Now the loss in kinetic energy is given by delta K is equals to difference in the kinetic energies of the colliding system before and after the collision. Here The kinetic energy of the colliding system before collision is given by half m1 u1 square plus half m2 u2 square minus the kinetic energy of the colliding system after the collision is half m1 v1 square plus half m2 v2 square, which is equal to half, which is taken from half is taken common as from both the terms, and we shall write half m1 u1 square plus m2 v2 square minus m1 v1 square plus m2 v2 square. That is delta k equal to 1 divided by 2 m1 plus m2 into m1 plus m2 into m1 u1 square plus m2 u2 square minus m1 m2 into m1 v1 square plus m2 v2 square. Let this be equation 3. Consider the term m1 plus m2 into m1 u1 square plus m2 u2 square. Multiplying the terms, we get m1 square u1 square plus m1 m2 u2 square plus m2 m1 u1 square plus m2 square u2 square. We shall write it this as m1 square u1 square plus m2 u2 square plus m1 m2 into u1 square plus u2 square. Adding and subtracting 2m1 m2 u1 u2 in the above equation, we have m1 plus m2 into m1 u1 square plus m2 u2 square equal to m1 square u1 square plus m2 u2 square plus 2 m1 m2 u1 u2 plus m1 m2 u1 square plus u2 square minus 2 m1 m2 u1 u2. That is m1 plus m2 into m1 u1 square plus m2 u2 square equal to m1 u1 plus m2 u2 whole square plus m1 m2 into u1 minus u2 whole square. Similarly, we get m1 plus m1 v1 square plus m2 v2 square equal to m1 square v1 square plus m2 square v2 square plus 2 m1 m2 v1 v2 plus m1 m2 v1 square plus v2 square minus 2 m1 m2 v1 v2. That is m1 plus m2 into m1 v1 square plus m2 v2 square equal to m1 v1 plus m2 v2 whole square plus m1 m2 v1 minus v2 whole square. Let this be equation 5. But we know that the initial momentum of the system is equal to final momentum of the system. That is m1 u1 equal to m2 u2 minus m1 v1 plus m2 v2. Also, E is equals to v2 minus v1 divided by u1 minus u2, which implies E square equal to v2 minus v1 whole square divided by u1 minus u2 whole square. That is v2 minus v1 whole square is equals to E square into u1 minus u2 whole square. Thus, equation 5 shall be written as m1 plus m2 into m1 v1 square plus m2 v2 square equal to m1 v1 plus m2 v2 whole square plus m1 m2 e square into u1 plus u2 whole square. Thus delta k shall be written as delta k equal to 1 by 2 into m1 plus m2 m1 u1 plus m2 u2 whole square plus m1 m2 into u1 minus u2 whole square minus of m1 u1 plus m2 u2 whole square plus m1 m2 e square into u1 minus u2 whole square. That is delta k, that is loss in kinetic energy, equal to 1 by 2 m1 plus m2 into m1 m2 u1 minus u2 whole square minus m1 m2 e square into u1 minus u2 whole square. Thus delta k equal to 1 minus e square into m1 m2 into u1 minus u2 whole square divided by 2 m1 plus m2. This is the expression for the loss of kinetic energy when the system undergoes inelastic collision. If the collision is perfectly inelastic, then the value of E equal to 0, that is the coefficient of restitution is equal to 0. Then the loss in kinetic energy will be given by m1 m2 into u1 minus u2 whole square divided by 2 into m1 plus m2. If the target body is at rest before collision, then the velocity of the target body u2 is equal to 0. In that case, the loss in kinetic energy is given by m1 m2 u1 square divided by 2 m1 plus m2. This is all about the loss of kinetic energy in case of an inelastic collision. In the next class, we shall discuss the conservation of linear momentum in case of a variable mass. Thank you.